Okay, I think we can get started. Hello, everyone, and welcome to the civil seminar. Today, I'm very pleased to introduce Dr. Julian Brimelow. Am I correct?
Brimelow.
Brimelow, sorry about that. Dr. Brimelow, who is a convective weather expert based in Edmonton. So as a quick background, Julian graduated from the University of Pretoria in South Africa with a bachelor's degree in meteorology back in 1993. He completed his master's degree at the University of Alberta in 1999 and then received his bachelor's from the University of Manitoba in 2011. He is a research scientist at Environment and Climate Change Canada and is working to improve the detection and prediction of hail and severe hail using radar products and data from Canada's numerical weather prediction models. So Julian has a broad publication record on various elements of deep convection, thunderstorms, hail, flooding, and drought. And before doing his PhD, his research focus was on modeling maximum hail size and severe thunderstorms. Julian has worked as a meteorologist for South African Weather Service, the British Antarctic Survey, and as a research assistant at the University of Alberta. So it's really great to have Julian with us today. He's obviously an expert in hail, and as some of you might have heard or read the news, we have the Northern Hail Project initiated at Western. So this talk fits well with this initiative. And with that said, I asked Julian to please start your presentation whenever you are ready. The stage is yours. Thank you very much.
Thanks very much, Reza. Good afternoon, everybody. So today I'm going to be speaking to something that might not sound that interesting because you'll be surprised how many people think this is a clear-cut issue. But is it possible to accurately estimate the fall speed and impact energy of hail? And I'm hoping I convince you why that's important and why it's still pretty much, I wouldn't say an open question, but something that we really still need to focus a lot of our research efforts on. So hailstorms are expensive. I don't know if you've been following the news lately, but in recent years, several hailstorms have caused $1 billion worth of damage, North America, Europe, Australia, and that includes Canada now. We had our $1.3 billion hailstorm in Canada, in Calgary specifically, back in 2020. And that was the fourth most costliest natural disaster in Canada to date. So because hail is a problem, obviously we need to understand the processes that affect the ability for hail to inflict damage on infrastructure, vehicles, crops. So we can hopefully adopt some mitigation measures to mitigate the damage. Now, to first order, I'm sure most of you know the damage potential for hail is largely governed by its fall speed. And because the kinetic energy of impact is half mv squared, so that v squared is obviously the main contributing factor. Now, although fall speed is a metric that we should, in principle at least, be able to estimate with a high accuracy, doing so for hail has eluded us for many decades. Research on this goes back to the late 50s and early 60s. So what I'm going to do today is I'm going to provide you with a history on some of the theoretical aspects of hail, fall speed, and impact energy, and also discuss some of the empirical relationships that we use to calculate the fall speed and impact energy. And I'm also going to discuss reasons why some of these methods fall short, why they're inadequate, and hopefully present a couple of ideas that might improve things moving forward. And I'm also interested to hear if any of you have ideas on how we can tackle this problem. So here are just some pictures showing what hail can do. On the left-hand side of the screen, those are pictures from the Calgary hailstorm back in 2020. And that day, the largest dimension of the hail was about 5 to 6 centimeters across. So, you know, not small hail, but not as big as it can get either. And here we have a Lamborghini that was probably written off because of the hail. Back windshield smashed in. And this here is at the bottom left is particularly problematic. We had new divisions in Calgary, in the northeastern part of the city. They have lots of vinyl siding. And as you can see, vinyl siding does not stand up to hail. On this day, not only was the hail relatively large, there were other contributing factors that made it bad. There was a lot of hail falling, and also there were strong winds. And I'll speak a bit about that later. But if you look carefully, you can see the wind. The wind was blowing the hail against the side of houses, and it actually broke some of the windows, in addition to just, you know, decimating the siding. And on the right here, top right, is another big problem with hail, and that's crop damage. It's quite a complicated relationship. It depends what kind of crop it is. It depends on what stage the crop is. But here it looks like it's probably a maize crop. It was in India that got destroyed by a hailstorm. And you can also see there's a lot of flooding here. So hail often comes is accompanied by heavy rain as well. And some of these hail swaths, as we call them, the hail swaths basically a contiguous area where hail was falling on the ground and causing damage. And here you can see the hail swath is seen from a Landsat imager. Here we just have RGB or true color. And these hail swaths can be anything from a few kilometers to hundreds of kilometers long, and anything from maybe 100 or so meters wide to tens of kilometers wide. It all depends. This is a particularly bad one in the Dakotas, in the northern Great Plains of the US. And you can see here, this is not immediately after the hailstorm. This is in the days following the hailstorm, because it takes time for the crops to, you know, the damage become evident as the crops start to die or lose leaf coverage, etc. And then if you look at a false color representation, you can see these pinkish areas are areas where there was hail that damaged the crops. So there are other reasons why knowing the fall speed and kinetic energy of hail are important. First of all, if you want to monitor hail, for the longest times, we've been using something called a hail pad, which is essentially just some expanded polystyrene foam. They come in varying sizes, but the typical size is 30 centimeters by 30 centimeters, although bigger is better. Nowadays, you'll see in these pictures there's tin foil wrapped on top of them to increase their sensitivity and also to protect the foam from the sun, because the UV rays damage the foam, and that affects the impacts or the indentations made on the hail pad during a hailstorm. But nowadays you can just paint them with white latex paint, and that works just as well. But for calibrating hailstones, if you have an indent on a hail pad, that gives you an idea of how big the stone is, but it's not one-to-one. So you need to do calibration. So what we normally do is we drop metal spheres or some very high density material, and we drop it from a known height that we know more or less matches, that'll create the same impact energy as a hailstone of that same size. And then we use a linear relationship basically to convert the indents on the hail pad to an estimate of the actual size of hail. So if we're going to do this, it's called the energy matching method. And if we're going to do the energy matching method, we need to know the full speed of hail, or as accurately as we can make it. The other reason the full speed is important is that if you're attempting to model hail or simulate it in a cloud model, the growth equations for hail, this equation here is basically the change of mass with time, is equal to the terminal fall speed times d squared, essentially. These terms here, this is it's basically amount of liquid water and ice in the cloud, and these are the collection efficiencies. But we don't worry about those for now. But I just want you to see that if you're going to model hail in a hail growth model, you need to know its full speed. And obviously, if there's a big error here, it's going to affect your growth rates, and that'll just, could degrade the forecast. The other reason why we care is if we want to do standard testing on building materials, we need to develop some standards, and then also need to develop different impact energies and velocities when we're shooting ice balls or ice spheres at, in this case, we have roofing. This is from IBHS. So they have actually a very fancy machine that can create replica hailstones of varying densities and sizes. And it's actually a really good machine because you can change the bulk density of the hailstone as well, which is really important. And you can fire at different velocities. But again, if we're going to fire, say, a 5-centimeter ice sphere at these shingles here, we need to be sure that the velocity it's hitting those shingles is close to what we can expect in nature. And you can see the damage here that we can cause to shingles from hail. Sometimes you just get a dent in the shingle. Sometimes you'll get granule loss, and that exposes the underlay, and then that can cause damage to spread. And then we can also even get cracks or breaches in the shingles. And these may not be too much of a problem in the short term, but with time, it means that your shingles are going to degrade even faster, and you're going to get water getting into them. And especially in the freeze-fall season, the following winter after the hailstorm, it can cause problems. The other thing you need to keep in mind with hail is that not all hail is equal in terms of its compressive strength. Now, what I mean there is, in this case, it's how hard they compress the hail before it breaks down. And you're looking at usually less than 1 megapascal before hailstones break. So this is a probability distribution function of the compressive strengths that they were using for the hailstones out of their lab. And depending on how firm or hard the hail is, or how resistant it is to being crushed, you can get different kinds of impact, from soft impacts to hard bounce impacts of your material. The other reason we worried about hail is that it can actually be really dangerous for people and animals. So the important thing to keep in mind here throughout this talk is that the impact energy scales with the diameter to the power of 4. So even a small change in the diameter of your hailstone has a disproportionately large impact on your impact energy. And research in Europe has found that for increasing hail size, if you're looking at living objects here, usually around about 4 or 5 centimeter, the probability of injuries being reported by people or being reported to animals starts increasing, and it just gradually increases above this 5 centimeter diameter threshold. For farmland and trees, it's a little more complicated because you might have a quick ramp up here to about 4 centimeters, and then after that point, it doesn't really make much difference how big the hail gets. You're usually going to get your crop obliterated regardless. So I think that explains this weird behavior for crops and trees for the really large sizes. Then if you start looking at non-living objects like greenhouses, roofs, car bodies, vehicle bodies, and windows, you only really start to notice things happening after about 3.5 centimeters. And I can speak from personal experience that our car got dented by hail that was about 3.5 centimeters in diameter when I was out chasing one day. So it is consistent with this. And obviously things just get worse as the hail gets bigger and bigger. And the thing to keep in mind is, like I said here, that as you get beyond 5 centimeters, the risk of injury increases, and fatalities are even possible for hail larger than 6 to 7 centimeters. And the reason for that is that the impact energy of a 7 centimeter hailstone is about 130 joules. Now, that might not mean much to us. I know I had to look into it. So just to give you some reference, a bike helmet's designed to withstand a point impact of 150 joules. So it's a lot of energy. And luckily, not too many people have been killed by hailstones, but I have seen pictures of people who've been caught in hailstorms and they're covered in welts from the hail hitting their body. So just to put this in context too, if you have 150 joules of energy, that's about equivalent to a fast ball, being hit by a fast ball in a baseball game. And there's a reason that the batters wear helmets, right? And so that it's a lot of energy and can cause a lot of damage. And obviously for smaller animals and for children, it's even worse. That you can lower that threshold quite a bit. So because of the potential for damage, a couple of people have come up with intensity scales for hail, similar to the EF scale for tornadoes. But here, the critical aspect is maximum hailstone diameter and energy. And you'll see these energy units, it's not joules, it's joules per square meter. So an individual hailstone might not have a very high impact energy. But if you integrate that over hundreds or thousands of hailstones hitting a square meter, that impact energy accumulates. And you'll see here that for complete damage to crops, you're typically looking at about 400 joules per square meter, depending on what there's research here out of France that I think was 300 joules per square meter. But basically, the idea is that the more hail that's coming down, the more accumulated kinetic energy you have of the hail, the more potential for damage. So, you know, a hen's egg or golf ball hailstone, if they're just here and there, are probably not going to cause too much damage. I mean, they will dent some cars and they might shatter some windshields, but you know, it's the integrated amount that's really important. So we have these two scales. One of this, an alpha is out of, I think it came out of Spain, and the Toro came out of the United Kingdom. And you can use these scales to attribute, you know, after the fact, kind of gauge how big the hail might have been and how much hail there was. This top right-hand picture here is from the Calgary hailstorm. And what you'll notice is the ground is completely covered with hailstones. And these hailstones were between 4 and 5 centimeters, most of them. So it's very rare to have that much large hail. So before moving forward, let's just do some quick background on terminal velocity. I know this is nothing new to most of you. I mean, the terminal velocity goes back to Newton's first law. You get your terminal velocity when the force from the weight of the object is balanced by the drag force, basically. And the drag force is the density of the medium it's falling through, the cross-sectional area A, the drag coefficient C, and the object's velocity squared. And if you want to solve for the terminal velocity, you basically just rearrange the terms, and then you get this equation here, 2mg over rho AC. So the heavier the hailstone, the faster it's going to fall. The denser the medium it's falling through, the slower it's going to fall. Or the higher the altitude, the faster it's going to fall. And the larger the cross-sectional area, it's going to slow it down. And if you increase the drag, it's also going to slow it down. So in meteorology, we tend to, we take this equation and we can have it in this form here on the top equation on the right-hand side there. But oftentimes we use the bottom right-hand equation where we write it in terms of the density of hail and the hailstone diameter, because most people don't measure the mass of hail when they're reporting it. Actually, I would prefer, and many of my colleagues would prefer, we weighed hailstones when we're reporting it and measured them, because collectively those two measurements give us a lot more information than just diameter or just mass alone. But out of habit, we've got into this habit of reporting the maximum dimension of the hailstone typically, and so we tend to use this equation on the bottom here. So that's one framework that we can calculate the full speed of hail. So all we need to know basically is the density of hail. It doesn't vary too much. It's usually between about 800 and 900 kilograms per cubic meter. Its diameter. And this is where things get a little tricky. Well, what's the drag coefficient going to be for hail? And I'm going to be talking a lot more about this coming up. So the other framework is a bit more theoretical. It's when you use the Reynolds number. I'm sure most of you have heard of that. And here we run into a bit of a problem. I prefer using the Reynolds number, and this is X here is the best number or the Davies number. The Reynolds number came about around about 1850. It was first proposed by Stokes. Sure you've not heard that name before if you're in fluid dynamics. But it was later attributed to Reynolds by a German scientist. And so your Reynolds number is basically your full speed times the diameter. And this parameter here is your kinematic viscosity. So your kinematic viscosity is just the resistance a fluid presents to flowing. So molasses has a high viscosity, and honey has also a relatively high viscosity, and then water has quite a low viscosity because it flows quite freely. But your kinematic viscosity is basically your dynamic viscosity or your absolute viscosity divided by the density of the medium. Just so you know what the terminology is here. So your best or Davies number is equal to your drag coefficient times your Reynolds number squared. But, you know, so we can calculate VT if we know RE. But to know RE, we need to know CD and X. Okay, can we calculate X at least? It looks like we can, because we have the diameter, the mass, and we know the density of the fluid or of air. We can calculate the viscosity, no problem, and the cross-sectional area for assume it's a sphere, it's all good. But the problem is then we don't know CD, the drag coefficient. So what scientists do is we found that if you look at log scale world, you can get a really good linear relationship between your Reynolds number and your best number. And that way we can, if we can calculate the best number, we can then infer the Reynolds number, and then we can calculate BT. So that's another framework that we use to calculate the full speed of hail, but it has the limitation that we have to, use this linear or empirical relationship. So speaking of the drag coefficient, as most of you all know, for smaller particles falling through air or water, initially the drag coefficient is quite high for the size, and that's because we have a laminar flow, so there's a lot of contact between your sphere in this case and the fluid or medium it's falling through. As you get into larger Reynolds numbers, so 20,000, a Reynolds number of 20,000 is approximately, that would from a 2 centimeter diameter hailstone. As your diameter or Reynolds number increases, your drag coefficient comes down. And that's because if you can see here, this is the vorticity of this is a CFD, computational fluid dynamics simulation of hail around a 1 centimeter hailstone. You can see you've got vortex sheets here coming off each end of the hailstone, and your turbulent flow is quite far downstream of the hailstone. So there's still here, your drag coefficient's relatively high. These are streamlined analysis. It looks like spaghetti in behind here, but note it's quite far downstream. As you get to bigger sizes, say 5 centimeters, your vortex streaks go away, your flow becomes a lot more turbulent and disorganized, and it moves closer to the hailstone. And this means that you have less contact of the flow with the actual sphere, and your drag coefficient decreases. And then it kind of plateaus for a while. And then this big dip here, this big dip here is where you get to critical flow. And that's when the flow becomes temporarily very turbulent around the object or the sphere, and your drag dramatically reduces, but it then bounces back again. And this happens at a lower Reynolds number for rough spheres versus smooth spheres. So here we have a very nice graph. You're going from about over 1.5, and then for 2 centimeters and larger, you're in about a 0.5. So it looks pretty good, right? So just to give you a brief history on calculating the full speed of hail. It started in the late 50s when scientists started looking into the hail problem, and then it accelerated into the 60s and 70s and 80s. But so this is basically just a summary of research papers that were published on the matter. And you'll notice we have, these data points, these are basically data points. So how many hailstones they do the lab tests or the wind tunnel tests with. And most of them are pretty small in sample size. This Matson and Huggins is the biggest one. It's a paper that came out over 40 years ago now. It was almost 550 stones. The other thing you'll notice here is the diameter range. Now, by definition, hail is a high density sphere that's at least 5 millimeters across. And what you'll see is that a lot of these, the range over which those tests were done, were less than an inch. There are some down here that are bigger, where they were using ice replicas. Macklin and Ludlam did a lot of testing using some ice replicas back in wind tunnels and dropping them from balloons. And they got up to 7.5 centimeters, but they didn't sample the smaller sizes. So on the right here is what they would do this is what they did in the Matson and Huggins. They would basically go out into the field in the summer. They would have a radio and somebody looking at the radar, and they'd say there's a hailstorm near this spot, and they would just basically drive into it. And the roof of the van had an opening in it, and then they had a rig set up inside with strobe lights and cameras, and they had a hail pad, and then they had the setup here to separate the hail from the rain and collect the hail. And using this high-speed photography at the time, here you can see the hailstone coming in, hitting the hill pad, and then bouncing off. So remember, this was 40 years ago, so the technology was nowhere near what we have now. They didn't have high-speed cameras. They had to use strobe lights to get the high-speed photography done right. But using some mathematics, some trig, and some ingenuity, they got this graph here, which is the vertical velocity of hail as a function of diameter. And they get a pretty good fit. There's some scatter, which you have to keep in mind. But this fit is pretty good. You're looking at error bars down here of about 1 meters per second, plus minus, and up here maybe not even 1.5 meters per second. So that's pretty good, right? The thing to keep in mind is this is only going up to 25 millimeters across, and hail can be up to 10 centimeters. The record largest stone that we've actually managed to collect and hold and measure and scan is 20 centimeters across. And that was in Vivian in the United States. So there's a big gap there. But I think at this point, it'd be easy to say, okay, we've got a pretty good curve, the end, we're done. You know, we've got this good fit and we're going to leave it there. But if only it was so simple, right? And because there's a problem. And if you look at the literature, I found over 20 equations in the scientific literature where they attempt to calculate the fall speed or terminal velocity of hail. And if you plot those, this is only a few here. It gets really noisy, obviously, because there's so many. So I basically focused on the upper end and the lower end, and then one in the middle. This red line here is one that's developed by Andy Hemsfield and Roy Rasmussen back in the late 70s. And, you know, for the longest time, this red curve was what we were using. Then in recent years, the IBHS in the States, they're a group who are funded by the insurance industry to develop and test materials for construction. They started collecting hailstones. They collected thousands of them, and they would measure them and weigh them. And on the larger ones, they had 3D scans using laser scans. And this curve started to get nudging down. This green line here is one of the first curves that came out of that paper. And, you know, if you're looking at a 5 centimeter hailstone, you're looking at a difference between about, oh, I don't know, 24 meters per second up to 35, 36 meters per second. That's a huge range of uncertainty. That's going to have a dramatic impact on your kinetic energy. In fact, your kinetic energy goes from about 15 joules for one stone up to 40 joules for one stone. So that's a large area of uncertainty. And even if you allow for the fact that, you know, you have quite a big range in fall speed here, so that's how we calculate the coefficient of variation. That's basically sigma, or your standard deviation, divided by the mean, right? This is basically because we're very small diameters, so it kind of falls apart, the coefficient of variation for very small sizes. But we have the sweet spot here between about 1.5 and about 3.5 centimeters, where we have pretty good confidence in the full speed of hail. But then above that, it just gets worse and worse. And you can see that in all these graphs. The spread increases dramatically as diameter increases. So this is not a good situation, because which of these curves is right? We don't know a priori, right? And all of these curves have some legitimacy to them. They were published, and there was some scientific rigor going on, but yeah, we have this huge uncertainty, and that's obviously problematic. Now, where is this uncertainty coming from? Well, the first thing to keep in mind is that hail is not spherical. But the purest definition of a hailstone is that it's a triaxial ellipsoid. So it typically has 3 axes. So it can range between an oblate spheroid, think of an M&M, that's an oblate spheroid, and then prolate spheroids. So a rugby ball, right, is a prolate spheroid, or a football. And if you look at the IBH data of those thousands of stones they measured, and you plot them as mass as a function of the maximum diameter, you can see here this red line is if you're the mass calculated using the maximum diameter. But you can see they track relatively close up until about 6 or 7 centimeters. Then above that, there's a marked deviation away from this red curve here. And that is because the larger your hail becomes, it tends to become more oblate, and even with the very large ones, they become more prolate spheroids. So the relationship falls apart, and you can no longer assume that hail is spherical. And this is a kernel density plot here, where you've got your aspect ratios, basically your minimum axis divided by your maximum axis. This is your intermediate, so your intermediate axis divided by your maximum axis if you're measuring two axes on a hailstone. So there is a hot spot. There is a tendency for them to be kind of in this area here, but we have a huge spread. And here are more pictures. The left-hand side here, these are hailstones that were collected by Barge and Isaac in Alberta. And you can see even the relatively small stones, some of them have quite a bit of structure. And this top left one, you can't even describe that as being spherical. It's more, grapple shaped almost. And then some of the big stones, like this top right one here, have huge lobes on them. And these lobes, they arise because if you have a small deformity on the surface of the hailstone, and it's in what we call the wet growth regime, it's growing very rapidly, there's a lot of liquid water in the cloud, these surface heterogeneous points become exaggerated, and you get these lobes growing. And of course, these stones aren't just falling like they are here, a snapshot in space and falling. They're tumbling, they're spinning, because there's aerodynamic forces on them. I'll get to that in a little bit. And that causes these lobes to radiate outwards. Now, obviously, this is going to affect your aerodynamics of your stone, right? This is no longer a smooth sphere. It's not even a rough sphere anymore. This is a completely different beast. And these are some nifty 3D laser scans. You can use photogrammetry too to create these 3D scans of hailstones. But you can see there's a large variety, and some are really smooth, others are quite rough. Others, like the bottom left here, have quite large lobes. So as you can see, it's hard to develop a framework that accounts for all of this, right? So let's go back to our nice, clean drag coefficient graph that I showed you earlier. The reality is, if you look at the bottom, it's not that neat. These are measurements from actual hailstones. Now, what they did here is they reverse engineered those Best and Reynolds equations to isolate the drag coefficient as a function of the Reynolds number. And you can see there's a lot of spread. And in fact, a lot of these points lie above this black line here. This black line pretty much is what we see on the top graph. So there's a lot of uncertainty, and that's because there's a lot of variability in the hailstone. Hailstones are almost like snowflakes in some respects. No two hailstones are really exactly the same. And you're seeing this here. And this points to a problem when you're trying to model hailstone fall speed. There's a recent paper published where they looked at thousands of stones from the IBHS that have been scanned and measured. These bottom two curves are theoretical relationships from CFD modeling or from other approaches. And the rule of the widely accepted rule is that for a smooth sphere, you're looking at a drag coefficient of about 0.45. And then for hail, anything between 0.5 and 0.6. But you can see here, this is again a kernel density, these contours. So we have this hot spot around 0.55, but there's a lot of variability, and even here we have a bit of bifurcation going on. You see these larger stones, we have an axis going up there, and then you also have an axis going down. So which one is it? And the spread here is ridiculous. And we go from 0.5 up to almost 0.8 for the drag coefficient. So the real world's a lot more complicated than the theory would assume. So can we mimic this? Can we make fake hailstones? We can make 3D prints of hailstones that have lobes and irregularities on the surface, and then we put them in a wind tunnel, a vertical wind tunnel. As it happens, there's a small wind tunnel in Mainz in Germany, but the problem with that wind tunnel is it's quite small, and you can only really fly, for want of a better word, hail up to about 5 centimeters across in them. Otherwise, you get too many effects from the walls, and the hailstone is going to move around, so it's hard to constrain it. So this is what a colleague of mine did, Thais et al., and they made these 3D prints of different hailstones with same size, but with different surface features to try and mimic natural hailstones. Now, if you look here, this is the thermal velocity on the vertical axis, maximum dimension on the x-axis. We go up to about 5 centimeters. This purple line here is a perfect sphere, smooth sphere, the full speed you would expect. So you're getting above 30 meters per second for golf ball hail. But then look, depending on what kind of lobes, if you have long lobes or short lobes, your velocity drops way down from over 30 meters per second to around about 23 meters per second. Again, that's a huge difference. So these hailstones are telling us there's something going on here. But again, which of these lines do you choose when you're modeling hail, and if you're trying to develop standards for lab testing, or if you're trying to grow hail? And it gets even worse. Obviously, these differences are exacerbated in the kinetic energy equation because it's d to the 4, or velocity squared. And you can see you're going here from less than 10 joules to for a sphere with Q6 long is what they call it, compared to a perfect sphere. Excuse me. So one experiment I tried with some colleagues was to look at really large hail. And for that, we used a vertical wind tunnel that is usually used by people for skydiving. And so here we have Vivian hailstone. This is 20 centimeters across, this bottom left white stone. And then we have some other 3D prints of stones that were printed to mass. So these weigh the same as the hailstone that was found in nature. This is about just under 900 grams, this Vivian hailstone. And I just want to, okay, it's going to work, I'm hoping. So we worked with this is in Denver that we did this, but there's now similar tunnels in Canada. And I want you to, this is the Vivian hailstone that you see. So the airstream going vertically is about 30 meters per second at this point. And at the beginning, there's very close matching between the full speed of the hailstone and the vertical airstream in the wind tunnel. But look what happens. That hailstone starts to spin and it lifts off, which means that something's changing the drag, or there's forces being generated, lifting forces being generated by the stone, the lobes on the stone, that are causing it to lift higher in the cloud. If in this instance, if we were in a cloud of the wind tunnel. And this is important because in a natural cloud, it's very turbulent. It's not a laminar, smooth flow. It's very turbulent in thunderstorm updrafts. Your stones are going to be, pushed around a lot. And if they start spinning, you can have different forces acting on them. You have this W here is the weight of the stone. So the stone's this ellipse here, and it's rotating here anti-clockwise. So you have torques that are either accelerating omega here, or they're working against it and damping it. You have a lifting force, this FL, and you have this drag force, which is acting the opposite direction of this vector here, V. And collectively, these forces can cause the stone to do very weird things. So when we're calculating the full velocity from those equations, when your drag force is equal to your the force of the stone's mass, they don't take into account any of these forces. So I'll leave it there for now for the full speed. And I want to speak about something else that's really important. Now, in thunderstorms, we oftentimes get strong winds accompanying the hail, right? There's downbursts, there's outflow boundaries, and the effect of wind on the impact energy of hail can be quite large. And it can cause a hailstone that was capable of reducing, say, 20 joules of energy to produce almost double that. And it also means that surfaces that are normally protected, say the vertical wall of the house, you have eaves protecting it. Because it's blowing at an angle, those surfaces are now exposed. And that's what we saw with the Calgary hailstorm, with the siding being decimated. So this is just a basic trick here. You have a hailstone falling at VT. You have a wind blowing from left to right at this speed. And then obviously your resultant flow, VR, is this. And it's no longer falling straight from vertical. Now, in addition to that, the wind is going to impart some energy on the stone. And that's going to increase its velocity. So to calculate the kinetic energy here, or you use this resultant, it'll be half mv squared, so it'll be half mvr squared. You have to take into account the wind and then also the full speed of the hailstone. This VD I'll get to in the next slide. This is from the downdraft. If there's a vertical motion, either up or down, but we're more interested in down. And this map on the right here just shows you that, as the wind speed increases, the kinetic energy for a given diameter is going to increase as well. So if you have if you say a 4 centimeter stone falling at about 25 meters per second, and winds of 25 meters per second, that's going to have about the same energy as almost a 4.7 centimeter hailstone. Now, here's just the same map before. So here we're adding in a downdraft too for a 2 centimeter hailstone. So if you add a downdraft, then you have this downward vector. So these are cumulative. And then you can see your VR vector becomes longer because now we've got this energy from the downdraft imparted on the stone plus the wind. Now, if you're looking at a 2 centimeter hailstone, if you have a 5 meter per second downdraft, you have a horizontal wind speed of 50 meters per second, which is not uncommon in a thunderstorm. You can easily get 90, 100 kilometer per hour winds. You're increasing your velocity by 50%. But remember, EK, kinetic energy, is half mv squared. So that is going to be a big increase in your kinetic energy and your damage potential. So as you can see, it's really complicated. And back in 1980, when Matson and Huggins, were driving around in a van trying to do high-speed photography, they did not have the technology that we have available to us today. But for some reason, between 1980 and now, there's been virtually no research. And that's why I had my slide there saying, ta-da, at the end, because that Matson and Huggins equation has been the one that's been used in most hail growth models, and also standards for impact for hail. But we can hopefully try and learn some more due to the miniaturization of electronics. And one thing we can do is, these days, you can build something really small. This little sphere here that you see being held in someone's hand is about 2 centimeters across. It weighs 7 grams. And in it, you have a battery, you have a microcontroller, you have an IMU, inertial measurement unit, and that can measure the axes that the object it's in is moving at. It's got a gyroscope and a magnometer. And this is less than 2 centimeters across. So you can cram a lot of technology into a small sphere. And then what you can do is you can take this large stone here. This is a stone from Australia. It's about 14 centimeters across. You can find the center of mass of this 3D stone. And you can then make a silicon mold of this, and then you can make an ice replica. And then you can cut that in half and make a little space at the center of mass where you can add this little device. And then what you can do then is we know more or less how high we have to go for a sphere, even with a higher drag coefficient, to reach its full speed. In this case, we've got a UAV here, got a 7 centimeter across hailstone, and we drop it. And we can have a radar at the bottom here. I'll speak about that just now. Or we can use the information from the onboard IMU to calculate not only how fast it was when it hit the ground, but also how it was behaving. Was it tumbling? Was it spinning? If it was spinning, what axis was it spinning around? And this stone is not going to fall straight down either. It's going to translate. And even if the wind was perfectly calm, it's still going to translate because of the irregular surface here. It's going to induce forces that are going to cause it to move away from the vertical. The other thing you do is high-speed photography. Nowadays, we have amazing camera equipment that can do much higher resolution than Matson and Huggins had. They can shoot at incredibly fast speeds and use technology that we can have very small exposures. So what you want to do when you're photographing a hailstone that's falling, you have to capture it in your frame of view at least 3 times. So then you can calculate the time between the images and the distance traveled between those images being taken, and then using basic maths, you can calculate velocity. But it's not that simple. To freeze the stone so there's no blurring, if it's falling at 30 meters per second, you need to shoot with an exposure of about 30 microseconds. And you also have to shoot at about 200 frames per second. And you need to use a wide angle lens. And why that's relevant is you need a large field of view, but that's also going to cause some distortion, which you have to correct. And then you need a camera that you can put in a waterproof or water-resistant housing. It's also going to be protected from the hail. And you're going to be storing a lot of images. And that's going to create a lot of files that are going to use up a lot of disk space. So this is actually quite easy to do in the lab. But if you want to deploy this in nature where you have wind blowing and you want to capture natural hailstones, it's actually quite difficult. And this is something that a couple of people have tried with mixed results. But I think it's definitely something that we need to work on more in the future. The other thing you can do is that there's a whole horde of new technology coming out related to autonomous driving. And one of those that's being used is miniature radars. So these are 24 gigahertz radars that they're putting on vehicles so they can use it to identify objects that they want to avoid, for example. And this radar here, as you can see on the right-hand side, the green, that's basically the size of a credit card. And I have one of these, and it has about a 30 by 30 degree field of view. This is looking vertically on the far right here. So it's got a fairly narrow beam width, looking up in the vertical. It can measure speeds up to 75 meters per second to within less than a tenth of a meter accuracy, per second accuracy. And the other neat thing is it can detect multiple targets. And the nice thing is it all runs in a Raspberry Pi. So it's easy to take this out into the field, put a polycarbonate dome over it, and point it vertically, and hopefully a hailstorm hits you. And last summer I managed to do this. So bottom left here are some of the stones that fell. That day was marginally severe hail. So the largest of these stones is about 2 centimeters across, which isn't very big. And this is one of the things we were wondering about with this, is how small the hail can it detect. And we know that it can detect at least down to 2 centimeters. And the other thing to note here is look at this guy on the top. That's not your typical hailstone shape. It's got 3 arms coming off it. The others are pretty much spheroidal, but you've got these oddities at the hail that collected. And here on the bottom right is just the time. So this is a time going from left to right that the unit was deployed at the beginning of my chase, and it was sitting in the back seat of the car looking out the back window of the hatchback, and you can see a lot of noise around about 0 meters per second. But this part here between where you see the arrow is when it was hailing, and it was measuring hailstones falling, and it was measuring fall speeds approaching 15 meters per second, well, more like 14 meters per second on this day. And this is quite low compared to what the theory would dictate. Now, what I didn't tell you earlier was when we did these experiments in the lab, in the wind tunnel, we were getting fall speeds that were 15 to 20% lower than what theory would suggest, and what some of those equations would suggest that I showed you. So it seems to be consistent that the fall speeds are lower than what we would expect. So we're hoping to do a lot more work with this little radar. I think it shed a lot of light on things. So that's all for today. So I'll just wrap things up really quickly here. Observation, modeling, and studying of hail are challenging. It's not an easy problem. There are numerous challenges that we have to face. And this is basically, as you've seen, owing to the complex nature of hail morphology. Its size, its shape, its roughness, its density, its how hard the ice is or how soft the ice is. And we have to take all these things into consideration if we're going to model the fall speed and calculate the impact energy. Now, we do have some technological advancements that can help us with this. And that's what we're hoping to do with the Northern Hail Project. There's going to be some great opportunities for grad students to explore some of these problems and hopefully shed some light on it. And I don't think it's a problem you're going to solve. There's not going to be one universal equation that explains all of this. They just plugs parameters in and it spits out a number that's always going to be correct. But hopefully we can at least reduce the error bars on some of those full speed graphs and on the impact energy. So thank you. And if you have any questions, I'd be happy to answer them.
Thank you very much, Julian, for the very interesting presentation. Okay, we have time for questions, but before that, I would just want to mention that students who have a class after this can leave the session. I won't take further attendance. Okay, I see a question from Farshad. Thanks for the presentation. Is there any consistency between the speed results obtained using the videography technique and the empirical equations? There's also a follow-up question on the chat. What if the size of the hail changes while falling to the ground, which can change the hail speed?
Okay, yeah, those are great questions. For the first one, the thing is, for those Matson and Huggins data, when they did use, essentially they used videography. They didn't call it that back then. They got a pretty good curve, like it had, the error bars were quite small, but compared to other empirical techniques, there's a lot of difference. So their full speeds tend to fall on the lower end of those 20 curves, those 20 empirical relationships or theoretical relationships. So roughly there is some consistency, but I think the telling part is it's towards the lower end, so lower full speeds for the hail compared to some of the other relationships. And I don't know if that answers your question or not. And the other question is, yeah, that's a good point. When the hail's falling or going up in the thunderstorm updraft, it's either increasing in size as it's growing, or it's as it's falling and melting below the melting level, it's going to start shedding water, melt water on the surface of the stone. And one of the things we don't take into consideration is we have a layer of water on the surface. It's usually less than 1 millimeter thickness on bigger stones. But even then, that's going to affect the aerodynamics somewhat. So yeah, you're right. We have to continuously adjust the full speed of the hailstone if we're modeling it to allow for the fact that the size is changing, the cross-sectional area, density, surface properties. And for the longest time, we just assumed that the hail's spherical. And it amazes me that we even get close to the right answer with some of these models, given all the assumptions that we have to make.
Okay, thank you very much. Other questions? So I assume, Julian, when there is a precipitation along with the hail, that can also cause some further issues, right? The functionality of the systems or some further damages. Do we have any evidence for that too? This is kind of a general question, not much related to your core of it.
I don't think that's been looked at much, no. But it probably will be a factor, yeah. Yeah, it's complicated.
Yeah, it is.
Yeah.
And it's interesting that to me, you're looking at this much detail of characteristics of the hail and how the shape of the particle can dramatically affect the overall damages, etc. But I assume there is also the other angle that matters too. For example, simply the number of these particles, the density of the particles within each square meters, right? But compared to what you're investigating, understanding those should be much easier, I assume, right, with the available instruments.
Yeah, I mean, right now we don't try and forecast the number of hailstones falling. So that Calgary hailstorm was a prolific hail producer of large hail, which is rare. Normally, if you're going to get that much hail on the ground, it's going to be smaller hail, like 2 centimeters, maybe 3 centimeters, or even like 1.5 centimeters to 2.5 centimeters, say. But right now, we don't have reliable techniques that can tell you, okay, today if there's going to be hailstorms, there's going to be a lot of hail coming out of them. And although they might not be very big, we don't have anything that can forecast ahead of time the accumulated kinetic energy. We just tend to predict, like Hailcast will just give you an estimate of the largest expected hail size. It tells you nothing about how much hail, and that's a problem. Yeah, and I don't know how we get around that.
Okay, thanks. I have a question from Angela, and then Gordon has also a question. Are you creating a database with a relationship between hail impact speed and weather conditions?
Not yet, but an exciting development is that as part of this Northern Hail project, they're going to be installing electronic distrometers in the city of Calgary. They're going to be deploying about 30 of them, and they'll be 3 to 4 kilometers apart. But with each one of those distrometers, so a distrometer is going to measure the number of hailstones and at the size, and the duration of the hail event. But next to that, we're going to have an ultrasonic anemometer. It's going to measure the wind speed. There's also a weather station that will measure the rain, temperature, and those aspects. So we're hoping that to gather data that you're mentioning, create a database of the hail impact energy and speed, and how that relates to conditions on the ground, the ambient conditions that accompany that hail. So yeah, that's going to be an important part of what we do.
Thank you. Gordon?
Yeah, thanks, Julian. Very good presentation. Can you hear me, I assume?
Yes.
Yeah, okay. Yeah, you were starting to talk about weather forecast, well, let's say hail forecasting, just as I was putting up my hand. So I'll just ask a further comment on this in the sense that, as you mentioned, the Calgary hailstorm, there was, what, $1.2 billion in insured losses. And I think I get the numbers exactly, but 500 or 600 million of that was to automobiles. And you just wonder if we could improve our hail forecasting through better science and observation systems. Would we be able to get more people to put their cars in a garage or not leave them out so they get blasted by hail? I know it's a bit hard to know, but I guess I'm just looking at the idea of combining information we give to people so that they better, let's say, are informed and warned where appropriate so they take actions.
Oh, definitely. I think that's something we're not leveraging enough right now, especially in North America with such huge urban centers like Dallas and Denver and Calgary. We know there's a lot of assets there that can be hit by hail. And so early in the day, we might have an indication that later today, there's potential for severe hail or especially large hail. But we don't know exactly where it's going to hit. So once the hailstorms do start to form and they are presenting on radar as looking quite bad, now we usually issue warnings. But in South Africa, for example, where I grew up, the insurance companies will email clients to say there's a hailstorm heading your way. You might want to put your car in the garage or take things out on the patio that could get wrecked by the hail. And they've had quite a lot of success with that because it gives people a heads up. I mean, people see the warning and they'll may or may not act on it. But if somebody's emailing you and saying or texting you and saying it's heading to your house, potentially, then you're going to be more proactive, I think.
Yeah, good. Thank you. And great presentation. Found it interesting. I used to study atmospheric turbulence, so those equations you were giving refreshed things that I hadn't seen in probably several decades. The Reynolds number. Thank you.
Dr. Najafi, you're
Automatically
unmuted.
unmuted.
Oh, sorry. So there's one other question by Isam. Yeah, using VIL as a hail proxy, what do you think is the critical value in kilograms per square meters that would cause a substantial damage? Also, how long the storm duration should be considered critical?
So the first part of your question, VIL was vertically integrated liquid water. Basically what you're doing there, for those of you who don't know, you're taking when a radar is scanning a thunderstorm, it scans it in 3 dimensions, and you can integrate the reflectivity, which is proportional to the number and size of hailstones in the sampling volume. And you can integrate that in the vertical, and that basically gives you some VIL, very simplistic terms. The VIL can give you a good idea as to how nasty a storm is in terms of hail, but it's not a great relationship. It doesn't scale well with hail size. I mean, larger VIL values do tend to be associated with larger hail, but not exclusively. And one of the problems with VIL too is that it's a function of air mass. If you have a warm, moist air mass, you're going to get higher VILs that may not that ordinarily would be associated with hail, but aren't in those environments. Likewise, if it's a cooler, drier environment, then you can have lower VILs that are associated with hail. So scientists have been using other metrics from radar to identify hail other than VIL. But still, we do use VIL. They're great for using it to track storms. The VIL is really great for tracking hailstorms, just to see how it's moving through time and space. But an average value, to answer your question, for cooler, drier conditions, as low as 25 grams per square meter to probably around about 50 if you're in Florida, for example, in the States, and subtropical, tropical environment. The second one, yeah, if we can forecast ahead of time what we call storm mode is, how the convection is going to organize itself. Is it going to be a supercell storm? Supercells are single cell storms with a rotating updraft. They tend to be long-lived, and oftentimes, not oftentimes, they can produce tornadoes, and they also tend to produce large hail. So, I think we have a pretty good idea nowadays about storm mode, although some might argue with me about that. But the thing is, if you have a supercell, they tend to be long-lived. So that can track for over 100 kilometers, last 3 hours, and it's just chugging along, and it'll cycle. It's not continuously producing really large hail or large amounts of hail, but it'll be cycling, but it'll create a long-lived hail swath, So I think that answers your question, I hope.
Yeah, the answer is yes.
Okay. Yeah.
All right. Thank you very much, Julian. Really appreciate your taking the time to giving this great presentation. I hope next time we'll host you at the Western and being physically present there. Yeah, I appreciate your time. Thank you, everybody. Thanks again, Julian. And yeah, wish you all the best and great rest of the day.
You too. Thanks a lot, Reza. And thank you, everyone, for attending. I appreciate the interest.
Thank you. Bye, everyone. Bye, Julian.